Well, hey there, Advanced Chem. I just wanted to take a couple of minutes, if you were struggling with those practice problems last night, to go over one of those similar in nature to the 2.2/2.3 number 1. Specifically one where I'm going to be using more than one part of this time temperature graph. So those tutorials were excellent. And in fact, this is exactly where that time temperature graph came from, but I thought I should at least go over one of these with you. And just as a heads up, today's quiz is not more than one part of the time temperature graph. You'll only use one part. On Monday, I'll do at least 2 or maybe more parts of the time temperature graph. So something very similar to what I'm about to go through with you right now. So here we go. It says how much energy will be released when 57.9 grams of carbon tetrachloride is cooled from 100 degrees Celsius and is completely frozen. And so here I have my time temperature graph, and I would suggest that the very first thing you do is figure out where you are at on this graph. Now, this graph is specific to water, but if we cross off temperature and we kind of ignore what's going on with temperature in terms of exact numbers over there, it's really generic for anything. And so this is carbon tetrachloride. We need some information about carbon tetrachloride to get started, such as at 100 degrees Celsius, what is it? And then what parts of this graph does it need to go through in order for that 57.9 grams to be completely frozen? And so that's what we're going to do first. That would be found on your reference sheets. So I'm going to slide over to that. And everything you want about carbon tetrachloride is in this table right here. It's about halfway down. And here's carbon tetrachloride. So it's got its formula, delta H of fusion, melting point, delta H of vaporization, and boiling point. So everything we need right there. So first of all, these are in degrees Kelvin, and so we're going to need to change our 100 degrees Celsius to degrees Kelvin to have those numbers to work with. So we're melting at 250, we're boiling at 350. So I'm going to go back to my time temperature chart and write that in. So this point right here, point 4, is going to be not at 100 degrees like it is for water, but this is actually going to take place at 350 K. And then its melting point down here is at 250 K. Okay, so these numbers just are only relevant to water. And it says it's cooled from 100 degrees Celsius, which I need to figure out what that is in Kelvin, so I just add that to 273, which means we're starting here at 373 K, which all in all means that I'm starting above. In part 5, I'm starting here at 373 degrees K. I'm going to have to go through 5, and then I'm going to have to go through, as it's cooled, I'm going to have to go through 4. Now, as it's cooling, this would be a gas then, because it's above the boiling point. So this would be delta H of condensation, which is going to be just the opposite of delta H of vaporization. Then it's going to have to go through being cooled. Once it condenses into a liquid, it's going to have to be cooled. Remember, anywhere you have these sloping lines, those are all going to be Q equals MC delta T's. And then down here, we're going to have to go through all of part 2 as well, and that's going to be the delta H of it's going to be frozen, so that's solidification. And again, that's just the opposite of your delta H of fusion. So we need to find our delta H of fusion and our delta H of vaporization and put the opposite values down. So looking at your reference chart, delta H of solidification there in green, that's the opposite of delta H of fusion. And so according to your chart, delta H of fusion is 2.67 kilojoules per mole to melt 1 mole of carbon tetrachloride. So our delta H of solidification would just be opposite and signed to that negative 2.67 kilojoules per mole. Number 4 did the same thing, found delta H of vaporization, which was a positive 30 kilojoules per mole. And since we're moving from right to left and it's condensing, it's going to release that same amount of energy. So now I am all set up, and this is a good thing to go in with a plan. So what I'm going to do now is take you in order from 5 to 4 to 3 to 2. And then all of those are going to add up to the amount of energy that's released during this process. So, got a lot of work to do. Here we go. We're going to start with section 5. I'm going to try to color code it. Start with section 5 of our graph. And in section 5, that is cooling as a gas. So we're going to use the Q equals MC delta T formula, where we need to find Q. Our mass is 57.9 grams. Our C I need to look up. And delta T is going to be, we're starting at 373, and this process is going to stop when we get to 350. Okay, so according to my reference sheets that I just slid over and looked at, carbon tetrachloride, this is in table R9, by the way. Carbon tetrachloride has a specific heat of 0.857 joules per grams degrees Celsius. So remember, at a constant pressure, Q is going to be equal to my delta H. I'm sorry, these two should be flip-flopped around. We should be getting a negative value as it is cooling down to indicate that energy is being released. Okay, so that calculated out, ignoring sig figs, I get that 1141.27 joules are released during that process. So then we can move on to section 4 of our graph, which would be the delta H of condensation portion. And that is going to be equal to our 57.9 grams of carbon tetrachloride. And it takes, let's see, 12 plus, oh dear, got to do the math on that. 12 plus, we have to have 35.45 times 4 grams per 1 mole of carbon tetrachloride. And then, according to the delta H of condensation, it's going to release a negative 30 kilojoules per 1. Well, it's not going to release a negative, but it's going to be releasing 30 kilojoules per 1 mole. Okay, so I got the molar mass there, and then calculating that all out, I get a value, again, ignoring sig figs, 12.25 kilojoules released in that process. Now, right away, I want you to notice we've got joules here in step 5 because specific heat is in joules per grams degrees Celsius, whereas down here we have kilojoules, so we're going to need to do some rearranging of units before we can be all done here. So I've gotten through step 5, gotten through step 4. Let's continue with step 3. Okay, in part 3, we have another Q equals MC delta T situation happening. And our Q is going to be equal to 57.9 grams again. Our C doesn't change, 0.857. And our delta T, we're going from 350 to 250 degrees Kelvin. So that's going to be negative 100. And so calculating that out, I get, again, ignoring sig figs entirely, negative 4962.03 joules. So that number being released during the process. And then last but not least, we have our, actually I think this should say 2. And so that is our delta H of solidification. And so we're going to start again with 57.9 grams. And now I know the molar mass is 141.8 grams per mole. And according to our chart there, is going to release 2.67 kilojoules for every 1 mole going through that process. And that comes out to be negative 1.09 kilojoules, so that much is released. And so again, kilojoules, and we've got joules. So the sum of all of these amounts of energy that are released is going to be my final answer. So what I'm going to do is take and put everything in kilojoules, I think that's easiest. And so what I have from my 4 little steps there is I have negative 1,141.27 joules, which would be 1.14 kilojoules. So I'll just go to 2 decimal places on my kilojoule since it looks like 3 sig figs is about what I should have anyways. Technically, with like my temperatures that I use, it looks like I should have 2, but I think on the chart they're actually 4. So I'm just going to go with 3 for now. And then we had a negative 12.25 for step 4. And then step 3 here, I'm gonna again divide by 1,000 here. So we've got 4.96. And then here in our last step, 1.09. And so it's the sum of all of those different amounts of energies that are released that gives us our final answer. And so adding these all up, I get a sum total of 19.44 kilojoules released during that whole process. So very cumbersome because we used 4 different parts of our graph, but just treating each individual spot in accordance with what's going on is how we get our answer. And some planning at the beginning really helps out with that. So I hope this helped. I hope this helps you get those practice problems done, and I hope you have a really awesome day. And I'll talk to you later. Bye.